Welcome back to the deep dive. Today we are heading straight down into the basement of chemistry.
Right down to a place where the normal rules of stability just don't seem to apply.
Exactly. We're going to be talking about materials that react to things so slight they almost feel, well, fictional.
And our subject today is a crystalline compound that is basically the definition of chemical anxiety. It's called fulminate silver.
So I want you to just for a moment completely recalibrate what you think an explosion needs.
Mm-hmm.
You think of TNT, you think dynamite, you're picturing a fuse, a lot of heat, a massive shockwave.
There's some big activation energy.
Right. With fulminate silver, you can just forget all of that. We are literally talking about a substance that explodes not from fire, not from a big impact, but just by being touched.
It really does sound like something out of science fiction, but it's a very, very real and incredibly sensitive chemical reality.
So our mission for this deep dive is to unpack the chemical architecture behind this compound.
Yeah, we want to understand the physics, the molecular strain that makes fulminate silver so incredibly sensitive that it's almost like the safety switch has been removed.
It's a fascinating and frankly terrifying study in just how much power can be packed into the wrong molecular shape.
It is. And the lessons here are really fundamental to understanding, the very limits of chemical bonding.
Okay, let's get right into that core paradox then, the whole contact detonation thing.
Yeah.
We have to really grasp how minimal the input is. I mean, when our sources say just touch, what does that actually mean on a physical scale?
It means the compound has one of the lowest known activation energies for any explosive material.
And activation energy is like the hill you have to push a rock over to get it to roll down the other side.
That's a perfect analogy. For something like TNT, that hill is a mountain. It takes a huge amount of focused energy to start that reaction.
And for fulminate silver.
As fulminate silver, the hill is barely a speed bump. I mean, the reaction is triggered by the tiniest amount of friction or pressure.
Like what, exactly?
Like the energy released when one tiny crystal just slides past or taps against another one. We're not talking about lighting a match. We're not talking about dropping a brick on it.
Right.
We're talking about microscopic vibrational energy being enough to shatter the whole structure.
That puts the danger into completely new context. It's not about mishandling it. It's about just existing near it.
Precisely. And the result of this extreme sensitivity is completely out of proportion to how much of the stuff you have.
So when the sources talk about a small point of it being enough,
They're talking about quantities in the microgram or maybe low milligram range.
which, to make that real for everyone listening, is like the amount of dust you might pick up on the tip of a needle,
Yeah,
a single particle.
yes. A literal snowflake-sized piece of this powder. And that tiny, tiny amount is enough to create a really disruptive, loud sonic explosion.
So not just a little pop.
Oh, no, not a puff. It's a sharp, forceful pressure wave because the material is so energy dense and it converts from a solid to a huge volume of hot gas almost instantly.
Okay, so we know the what touch equals boom. But the deeper question is the why.
Right.
What is it about the molecular geometry of this silver compound that makes it, a ticking time bomb?
This is where we have to look at the unstable chemical bond itself. We're moving from the physical trigger to the chemical reason.
And the culprit is something called the fulminate ion.
The fulminate ion. It's AgCNO. So you have silver bonded to carbon, bonded to nitrogen, bonded to oxygen. That CNO chain is where all the tension is.
And what's wrong with that arrangement? Why is it so stressed?
The atoms in that chain are just. They are fundamentally unhappy. They're being held together in a really rare and strained configuration, which gives the molecule a huge amount of stored potential energy.
They want to be something else.
They desperately want to be something else. They want to rearrange into super stable things like carbon monoxide and nitrogen gas.
So the molecules themselves are already like on a hair trigger, constantly trying to tear themselves apart.
That's the perfect way to put it. And that slightest vibration, a touch, a tremor, it provides just enough kinetic energy to snap that first unstable bond.
In winks one goes.
A chain reaction. The whole thing starts to decompose, releasing all that stored energy almost instantaneously.
So let's connect that back to the loud sonic boom. You said it was about the solid converting to a gas.
Yes,
Okay.
and this is so critical to understanding the blast. When that AgNO structure just collapses, it instantly turns into solid silver and two very stable high-volume gases, carbon monoxide and nitrogen gas
So you're going from a tiny compact crystal.
to a massive cloud of hot gas in a microsecond. Yeah,
Wow.
you get this instantaneous phase change. A milligram of solid suddenly becomes thousands of times its original volume. That rapid expansion is what creates the intense pressure wave. That is the sonic
So
explosion.
speed is the key.
The speed is everything. It happens so fast, the energy has no time to just dissipate. It has to express itself mechanically, violently.
That just makes it so brutally clear. Okay, this brings up a huge question about the danger quotient.
Since the power is so immense, what are the specific warnings about actually handling this stuff?
Well, because the initiation threshold is so low, the risk just scales terrifyingly fast. The sources warn that even expert scientists, people who work with explosives for a living, they only handle it in millimeter
The
quantities.
millimeter quantity.
They're working with piles of powder you can barely even see.
Think about that. I mean, if the experts are measuring safe handling in the size of a pinhead, that tells you there is absolutely zero margin for error.
None. And that leads to the starkest warning in the source material,
Which is,
that the consequence of having even a small bag of this stuff would be catastrophic. A huge, devastating explosion.
we're not talking of, losing a finger.
No, we're talking about structural damage to a building. Severe risk to life, well beyond the immediate area.
It's sobering to think that just going from a dust particle to, say, a thimbleful moves it from a chemical curiosity to an uncontrollable weapon. It really reinforces that the power is just baked into the chemical structure itself. It's perpetually unstable.
So with all this extreme risk, you have to ask, why? Why would anyone have bothered to create or use something so volatile?
Historically, there was a market for that exact property, for that extreme sensitivity. Fulminate silver was valuable because it wasn't stable. It served as what chemists call a primary explosive.
Meaning it's the thing that starts the bigger explosion.
Exactly. It's the spark. It's the material used to set off a larger, more stable secondary explosive, like TNT or gunpowder.
Ah, okay.
Because it needs almost no energy input, it was perfect for things like percussion caps or ignition systems, where a tiny mechanical shock had to translate instantly into a high-energy pulse.
So in fireworks, for instance, if you wanted that instant, sharp crackle,
Fulminate silver would give you that rapid, efficient initiation. It was used in certain components that needed that instant snap.
but obviously its use just plummeted.
Drastically. The drawbacks just started to massively outweigh the benefits.
That it wasn't just the danger, was it?
It was a compounded danger, really.
Yeah.
First, the extreme sensitivity meant it was a constant risk to make, to transport, to store. But second, it's also very sensitive to moisture, and it degrades over time, sometimes becoming even more volatile.
So it's unreliable on top of being dangerous?
Absolutely. And then safer, more predictable alternatives were developed, like lead-azide. They offer a similar low activation energy, but they're far less twitchy when it comes to friction and impact.
So in short, there were just better, safer tools for the job.
Exactly. Which is why you just don't see it in commercial applications today.
So where does it live now? If it's too risky for commercial or even, military use, is it just in research labs?
It is entirely restricted to specialized laboratories.
Yeah.
And even there, it's only handled under the most intense and strict supervision you can imagine.
The control must be twofold, right? Like specialized equipment.
And specialized protocols.
Yeah.
Equipment designed to completely isolate the researcher from the material. And protocols that rely on remote handling whenever possible to minimize human contact entirely.
You can just imagine the safety briefings in a lab where a millimeter is considered the maximum safe sample size.
They treat it less like a chemical and more like an elemental force that has to be contained at all costs.
That respect is definitely earned.
It is. It's a phenomenal case study in the thermodynamic boundaries of stability. There's a compound sitting right on the absolute edge.
Okay, so let's synthesize this. In this deep dive, we started with this paradox, an explosive that detonates by touch, and we've drilled down into that unstable adjacent bond, which allows a single crystal bumping into another one to trigger this massive instantaneous expansion into gas.
And the science is undeniably frightening, but it's also just deeply engaging. It shows you the immense power hidden inside molecular structures.
We've really confirmed that stability is a very fragile concept in chemistry.
It is. A tiny input can lead to a catastrophic output, all because atoms want to find a more comfortable, lower energy arrangement.
So here's our final thought for you to ponder. If simple physical contact, a mere vibration, can unleash such devastating power from an unstable chemical bond like this, what other incredibly volatile yet hidden sources of energy exist in the chemistry of the everyday world that we just take for granted? Are there molecular arrangements in new materials, maybe industrial processes, that are also teetering on that same precarious edge, just waiting for the one vibration we haven't accounted for yet?
The search for perfect stability and knowing where those limits are, that remains one of chemistry's most compelling and most dangerous frontiers.
Thank you for joining us for this deep dive into explosive chemistry. We'll see you next time.